We interrupt your usual programming for a 5-minute news flash. Nanotechnology-Enabled Drug Delivery Systems, or NDDS, is a new technique that uses nanoparticles to deliver medicine. Researchers believe this will lead to better, cheaper medicine. In today's segment, I'll answer all of your questions about NDDS. Nanotechnology is the manipulation of matter on the scale of nanometers, a length 100,000 times less than the width of human hair. NDDS are generally between 10 and 1,000 nanometers long. They are formed by two components, an active ingredient and a delivery system. The active ingredient has effects on living matter. Meanwhile, the delivery system contains the active ingredient and manages when and where to release the ingredient. On the left, you see a diagram of a nanometer scale system. The pink molecule is the active ingredient enclosed by the orange capsule. On the right is a false color transmission electron micrograph of liposomes, spherical nanoparticles that can be engineered to deliver drugs to specific cells in the body. This method of viewing nanoparticles uses a beam of electrons and colors added later to help distinguish between separate parts. Liposomes are made of phospholipids, like a cell membrane. Since the nonpolar tails of the phospholipids are hydrophobic or water-fearing, they are sandwiched between the polar heads, which are hydrophilic or water-loving. This creates a container for medical ingredients. Here's an example of NDDS. Nanoparticles can be disguised as red blood cells, which don't trigger the body's immune responses and deliver cancer-fighting drugs directly to a tumor. The red blood cells camouflage. This system mimics the body's natural drug delivery behavior by creating vehicles that can live and circulate in the body for extended periods, safe from the immune system's attacks. The cell membrane is such a powerful shield because of its chemical composition. It is formed with a lipid bilayer, which consists of 3 layers that have different polarities: a polar head, 2 sets of nonpolar tails, and another polar head, or 2 layers of phospholipids. Due to the extremely dense packing of the long nonpolar tails, the London dispersion forces are especially high. This makes normal penetration of the bilayer nearly impossible for larger molecules that are used in the immune response. Whereas a free nanoparticle can circulate for minutes and a normal NDDS can circulate for hours, a red blood cell shielded particle can circulate for nearly 2 days. Another example is a project to deliver doxorubicin to breast tumors. For decades, the best NDDS could only deliver 1% of the drug to the intended target. A team at MIT designed a new system that uses nanoparticle communication, creating a 40-fold increase in drug delivery. The team used the blood coagulation cascade, which occurs when the body detects injury to a blood vessel. Proteins in the blood called clotting factors create strands of fibrin to seal the injury site. The presence of cross-linkages make fibrin very strong. Essentially, a glutamine group is bonded to a lysine group, which leads to a stronger structure thanks to the isopeptide bond between the 2 amino acids. An isopeptide bond being a bond between amino acids that is not present on the protein's main chain. To use the cascade, the researchers needed both signaling and receiving nanoparticles, S and R for short. First, S particles exit the bloodstream and arrive at the tumor site via tiny holes in the leaky blood vessels that surround tumors, the same way most nanoparticles reach their destination. The S particles then emit heat to trick the body into thinking an injury has occurred or bind to a protein that starts the coagulation cascade. Then, R particles are coated with proteins that bind to fibrin, which attracts them to the site of blood clotting. These receiving particles carry a drug payload, which they release at the site of the tumor. This uses the actual environment that the tumor causes instead of trying to directly target the tumor itself. How? Because it is targeting the leaky blood vessels caused by the tumor. The rapid research in nanoparticle drug delivery means 4 main advances. First, the systems being produced now can specifically target cells based on chemical signals. The size and low amounts of interference with metabolism lowers the toxicity normally seen to treat certain diseases. These products also lead to more safe and biocompatible techniques for treatments. Finally, it also facilitates faster development of new medicines. These 4 traits dramatically improve upon traditional medicine and will lead to a smarter future. NDDS seems very promising, but any specific economic and societal impacts can only be speculated for now. NDDS are not 100% tested for toxicity and therapeutic effectiveness. As such, scientists are unsure whether to invest in development. On the economic side, NDDS are definitely going to be a big hit in the medical industry. NDDS is expected to have a total market of $136 billion in 2021. However, large-scale manufacturing and clinical and patient perspectives of NDDS have been forgotten because the current priority is just researching the performance of NDDS. Meanwhile, on the societal side, there's a debate over what regulatory procedures are needed for NDDS. So far, the European Medicines Agency and FDA consider our present methodologies to be sufficient for identifying potential hazards. Another societal issue that is more convoluted is intellectual property rights. As an AstraZeneca scientist argued, patents for NDDS will be hard to defend because many colloidal patents already exist, colloidal meaning a particle of one substance dispersed through a second substance. These kinds of legal disputes will likely be prevalent in tomorrow's society. Finally, let's take a look at some of the Canadian breakthroughs in this field. At University of British Columbia PharmSci, they are researching advances in NDDS technology. One of their advancements was an improved method to encapsulate sterosporine, a water-insoluble drug, into lipid-based nanoparticles for drug targeting through tumors. The encapsulation allowed mice to aggregate 3 times the sterosporine with lipid-based nanoparticles than free sterosporine itself. This led to nearly complete growth inhibition of a multi-drug resistant breast tumor, while free STS sterosporine only exhibited moderate activity. As you can see, the field of NDDS is still very undecided and is still in the process of research, but it is a promising area of research. With virtually no environmental or societal impacts due to the tiny scale of this medicine and the many benefits to the medical industry it poses, NDDS is sure to be the next big medical advancement when it hits the shelves in bulk.